Okay. Okay. So what is one-shot information theory? It is the setting where a resource can be used exactly once. Okay. So an information theoretic resource, for example, can be a source to be compressed. So the source outputs symbols according to a probability distribution. Okay. So this source has to be compressed. Normally, the raw symbols require a lot of bits to be expressed fully, but I want to compress them to a smaller number of bits so that if required, the original output of the source, the original message can be recovered, and the probability of error is very small in the process. So that's the problem. And another very common information resource that we will study is a noisy channel for information transmission. So this intuitively is very clear. So there is something, let's say, like an optical fiber, and there is a sender, Alice, who wants to send a message. So the message has to be first encoded into a slightly larger string, let us say. So this is the code word which is sent to the channel. The channel puts in noise, but because of the redundancy in the code word, the decoder and the output of the channel can decode and infer what was the message to be sent. So we want the error in this entire process to be small, as kind of stuff. So in the one-shot setting, this resource can be used exactly once, no more, no less. This is in contrast to the traditional setting, which you may have seen in your earlier courses. So the same resource can be used n times independently, and n is large. So this is what we will call the asymptotic IID, independent and identically distributed setting. So the traditional information theory from the time of Shannon onwards has been done in the asymptotic IID setting. But in this day and age, we will do things in a new style, and you'll see this style has a lot of cleanliness and a lot of advantages. So we will do this information in the one-shot setting. That's what the course is about. Some of you may be aware that there is another setting, not so well known, which is called the information spectrum setting. So there, the alphabet sizes grow to the power of n. So it is, in this aspect, it's like the traditional setting where the same resource is used n times. So let us say there is a source which I want to compress. Now the source, let us say, has the alphabet size k. The source is used n times independently. So now the alphabet size becomes k to the power n. So in the information spectrum setting, there is this parameter n which is growing. The alphabet size will be k to the power n. Okay, so k is the base alphabet. So the alphabet sizes grow exactly as in the asymptotic IID setting, but the resource varies arbitrarily with n. Okay, and n is large. So what do I mean by that? Let's go back to the source. So in the IID setting, the source has an underlying probability distribution. So there's a probability distribution on k, and the probability distribution that I'll take on k to the power n will be n IID copies of the probability distribution on k. So sometimes I'll call it as the tensor power distribution on k. Okay, so it is k repeated independently and identically n times. But in the information spectrum setting, there's an arbitrary distribution on the alphabet of size k to the n. Okay, and there is no connection between the distribution on k to the n and the distribution on the alphabet k to the power n plus 2. So this is the difference. So this is what I mean by the resource varies arbitrarily with n. Now we let n go to large and we look at the rate per resource use. So this is called the asymptotic non-IID setting, and it was pioneered by Han. Now, one-shot setting is the most general one, as you will see. It implies results in the other two settings. Okay. Okay. Let us start off with maybe one of the simplest and the most basic tasks in information theory. So let me remind you, this goes by the name of Shannon's noiseless source coding theorem. Okay. So in this, there's a source S which outputs a symbol little s with probability PS. Now we are in the asymptotic IID setting, so S is used n times independently. So we will refer to it as S to the tensor power n. So this is the source at the nth level. Okay. The probability distribution is just n IID copies of PS. the distribution P is known to all encoding decoding parties involved. Okay? Now fix some two parameters epsilon and delta between 0 and 1. Then for large enough n, so how large enough? It depends upon the sources. It depends upon the probability distribution on S, the base probability distribution. It also depends on epsilon and delta. Then for sufficiently large n, there's a deterministic encoder E that compresses a sample from S to the tensor power n to a certain number of bits. So let's look at the picture. So there is this encoder. So what it gets n symbols. So the source S is used n times independently. It gets n symbols. Now, if I were naive, I will say that to represent one symbol, I take log s bits. So to represent n symbols, I'll take n times log s bits. But I don't want to do that. I want to encode them. I want to compress them. So the output of the encoder is a compressed version of the input, so which I'm calling it as E of S1 to Sn. Now the point is, this E is supported on a much smaller number of bits. So instead of n log s, it is n times a quantity which I will define shortly, called h of s, the entropy of s. And there is a theorem which says that the largest value of h of s is log s, but usually it is much smaller than that. So this is where the savings has been got. So instead of n log s, I compress down to approximately n times h of s. What is the precise theorem? So I can compress to n times h of s times 1 plus delta. So there is a little fudge, 1 plus delta. Okay. And now there's a deterministic encoder that recovers the original sample for a 1 minus epsilon fraction of the samples under the distribution PS. So note that there is this underlying probability distribution on these samples, which is coming from PS repeated n times. Now, some of these sequences will be decoded incorrectly. Like all the sequence will be encoded into n times hs bits, but some of them will be decoded incorrectly. But nevertheless, most of them will be decoded correctly. So 1 minus epsilon fraction of the samples will be decoded correctly by the decoder. So this is the achievability of Shannon's noiseless source coding theorem. So source coding means this is the source. Its outputs have to be compressed. And noiseless means that after the source is compressed, so if I look at this string does not suffer any further noise. There is no noisy channel which acts on it. So this string is available for posterity for the decoder to act on. Okay, so that's the nomenclature. Okay. So the achievability, I know one can compress down to nhs times 1 plus delta. But there is also converse. So any randomized encoding and decoding strategy. So I'm emphasizing private coin. What do you mean by private coin? The randomness used by the encoding strategy and the randomness used by the decoding strategy here are independent of each other. So it's as if they toss their coins in private and carry on their respective encoding or decoding algorithms. Okay. So a public coin would mean that the encoder and decoder use the same coins. So we are not allowing that. The encoder and decoder are completely independent of each other. And this is like the usual information storage setting. So the encoder and decoder might even act on different days. So they are completely independent of each other. They're allowed to use private coins for their internal randomness for their purposes. So the converse says that any private coin randomized encoding and decoding strategy that succeeds with probability at least 1 minus epsilon uses almost nhs bits, but you can see the fudge here. It is now nhs times 1 minus 10. So this is Shannon's theorem. And what is entropy? Entropy is this function, negative log summation over the symbols s, ps, log ps. So I'll always take log to base 2 in information.
Are there, so I have a question, sorry. Yeah, so are there public coin protocols known where the compression is more?
No. Okay, but at least not that I'm aware of, and I would think if I can prove a converse in the public coin setting, but yeah, but anyway, for this theorem, let us say we will not think of public coin protocols. Yeah, and in fact, no, even public coins will not help in this case. Okay, so I think one can prove that. Yeah, but that we can discuss offline, or we can discuss in the Slack channel.
Yeah.
Yeah, but yeah, right now we are only talking of private coins. So is the setting clear? This is the time to ask questions. Okay. No, so let's yeah. Okay. So let's go on. Okay. So here is a brief recap of the proof, as you may have learned in your traditional information theory course. So I will not be proving all the little statements out here, but this is how it goes. This is for memory. If you don't understand what this means, don't worry. This is the one-shot setting, so we will do this differently. Okay, so the traditional proof goes by the concept of what is called typicality. Now, people who have done information theory course, you may have heard two types of typicality: weakly typical or strongly typical. So it is nicer to work with the second definition, strongly typical. So what does that mean? So let me define it precisely. I'll call it something to be delta frequency typical, also known as delta strongly typical. So what are these? These are sequences. So this is a sequence of n symbols. Okay. Shorthand for sequence of n symbols will be this, s to the power n. So in this sequence, every symbol s from the original alphabet appears how many times? N times ps times. So let us say if this sequence was chosen in IID fashion from the base probability distribution, then I'll expect that a particular symbol little s appears around n ps times. Right? So this is formalized the concept of typicality. The sequence is typical if every symbol occurs roughly n ps times. And again, there is this fudge to make it precise, 1 plus minus delta. So the number of times it appears lies between these two extremes. And the moment you have a typical sequence, we can ask what is the probability that a random sequence from the IID distribution is typical. So you can use whatever you like, law of large numbers, Chebyshev, Chernoff, okay, to conclude that for large enough n, typical sequences consume at least probability 1 minus epsilon. So most sequences from the IID distribution are typical. Okay. And furthermore, you can also prove that the log of the number of typical sequences is roughly n times h of s. So it's between these two quantities. And conversely, any subset of sequences, okay, so remember there are lots of sequences. So the number of sequences is 2 to the power n log s. Okay, so if you're looking at the log of number of total sequences, that is n log s. That is exactly what we had at the input here, n log s. But the typical sequences are much less. It is not n log s, but it is something type, something like n times hs. Okay. And you can sort of see where this n times hs is coming from here. Okay. Now, conversely, so in fact, the conversely statement is used to prove the converse of Shannon's noiseless coding. So conversely, any subset of sequences of 1 minus epsilon probability will intersect with the typical sequence set. Okay, and the intersection will have size at least 1 minus 2 epsilon. That's fairly easy to see. It's just the union bound. I have an arbitrary subset which misses out epsilon fraction of sequences. The typical set also misses out epsilon fraction of sequences. So the intersection of my subset with the typical subset should be at least 1 minus 2 epsilon. Okay. Moreover, every typical sequence has probability approximately 2 to the minus n times h of s. Okay. In fact, this last statement that the probability of every typical sequence is roughly 2 to the power minus n times hs is what goes into proving that the log of number of typical sequences lies between these bounds. So these are things which you can even prove offline. Okay, they just use the notion of frequency typicality. The proof becomes very simple if you use this notion of frequency typicality. Okay, and to show that these typical sequences consume 1 minus epsilon probability, you have to use something like law of large numbers or stronger quantitative versions. Any questions about this? Okay, let's go. Okay, so now
I have one question. Sorry.
Yes.
Why this is like plus minus delta? Like, I mean, Shouldn't
So
it be like
the number of typical sequences is upper bounded by n times 1 plus delta hs and is lower bounded by n times 1 minus delta hs. Okay. So this is just a shortened notation to say that this number lies between two bounds.
Okay.
Okay. Similarly for this probability, like all the typical sequences don't have exactly the same probability. They have slightly varying probabilities, but the probabilities lie between these ranges.
okay.
So that's all. Yeah. So and again, if you come up with what is achievable, we know we can compress down to this much, n hs times 1 plus delta. We know that any compression strategy will require at least this. So there is some gap, okay, out here, which is related exactly to this lower and upper bounds. Okay, so if you see the proof from, let's say, Cover and Thomas, any standard classical information theory book, okay, so they will sit and prove all this and then show that. You see that exactly this plus minus delta here translates to the plus minus delta here. Okay. More questions, please? Okay, so let's go. But today we will not see the proof of Shannon's theorem in detail. Instead, we'll try to do this in the one-shot setting. So this is an invitation to the one-shot information theory. So in the one-shot noiseless source coding problem, I still have a source. It outputs symbol S with probability PS. But S is allowed to be used exactly once. Okay. And now, whereas in the IID setting, S was used n times independently and identically. Okay, and there was the encoder, and we know we can go down to n times HFS bits. Okay, from n log S, we can go down to n times HFS. So now the question is, what can you do here? The input is log S. How much can we go down? So what is this? So there is this epsilon. So how far can a private coin encoder compress S so that there is a private coin decoder that recovers the original sample with probability at least 1 minus epsilon? Okay. So this is the question. And note that the probability is measured with respect to the private coins of the encoder and the decoder and the randomness of the source S. So I will pause the recording here, resume recording. Okay. Okay, so sorry about that. So is this strategy clear? Achieving H epsilon max S, maybe plus 1. This is very crucial. Okay. So very nice, Ishan. So this is essentially optimal, as we will see. Okay, just this naive strategy. So now let us try to prove the converse. So so remember, I allowed randomized encoding, randomized decoding. So life becomes a little complicated. So any private coin encoder can be thought of as a probability distribution, okay, on the encoding code word E that depends on the source sample S. So I will denote it by P of E given S. Right? So S is what is input to the encoder, and the output of the encoder, what I'm calling ES here, is a probability distribution on E. So it outputs a symbol E according to this marginal distribution, this conditional distribution. Okay. And what is the private coin decoder?
Just one second. So this small e is a sample from the distribution from the marginal capital E distribution, right?
No, small e is a symbol from the code word space. So remember, the code word space eventually, as you'll see, will be H max epsilon S bits. Okay.
No, I'm just wondering what the joint distribution is on the source along with the code words, right?
Well, I've not defined a joint distribution, so let's go slowly. Okay. So
okay.
I've not defined any joint distribution. So there is, of course, an underlying distribution of the source PS. Now I'm saying any encoding strategy can be mathematically formalized by P of E given S. Okay, that's all. And E is from the code word space, and the size of that space, the log of the size of the code word space is the number of bits to which I'm going to compress. We'll see what it is later. Okay. And similarly, any private coin decoder can be thought of as something like this. So remember, the decoder receives a code word symbol E, and it has to output a guess of the source, which I'm calling S hat. Okay, so guess sample S hat. It depends on the code word. So the decoding strategy can be given by another distribution like this. And what we want to minimize the size of the code space. So I want to minimize mod E such that this overall probability, so this is the total probability of success. Okay, so what is the probability of success? The source outputs a symbol S with probability PS. It goes to the encoder, which outputs E with probability P of E given S. Then it goes to the decoder, which outputs S hat with this probability. But if I want it to be correct, the decoder better output the same S. So this is what I've written out here. So this grand summation should be larger than 1 minus epsilon. Okay, so this is the overall joint problem. Is it clear to everybody? What's the joint probability of success? Okay. So this has to be larger than 1 minus epsilon. And from here, I want to conclude that log of E is larger than H max epsilon S. So let us see how it goes. So let us give a name to the quantity inside this big brackets. Okay. So let's call that lambda S. What is lambda S? It has a nice interpretation. It is the probability of decoding S correctly. Okay, S has been input to the encoder. What is the probability that the decoder also recovers the same S? So whatever it is, it's a number between 0 and 1. Okay. And furthermore, what I see, what is the summation lambda S? So you can do this jugglery, and you can see that summation lambda S is less than or equal to mod E, the size of the code word space. And what do we know? It is the same expression which I've written in terms of lambda S. So I know that the average of lambda S over PS is at least 1 minus epsilon. That is the correctness required. Is this slide clear? Okay. So actually this, proving a lower bound on mod E is essentially studying a linear program. Okay, so what is the linear program? It's something like this. I want to, so remember that E is lower bounded by the summation lambda S. So let us study a slightly different problem. Let us try to minimize summation lambda S such that the success probability of decoding correctly is 1 minus epsilon. And what is the constraint? Remember, lambda S lies between 0 and 1. Okay. So whatever minimum value I'll get for this optimization problem, that minimum value will be a lower bound on E. Okay, on the achievement. Is this clear to everybody? Is this clear what strategy I'm going to follow? Okay, good. So here comes the difficult part. So we can show without loss of generality that to minimize summation lambda S, it pays to set lambda S equal to 0 for the smallest coordinates whose probability sum to at most epsilon. Okay. Now let us say what I mean by this. Okay. So Zishan said, let me arrange the probabilities in descending order. Okay. So these are the probabilities. Okay. And let us say these are the smallest probabilities at the very tail. Okay. So these are the smallest probabilities at the very tail. Now, so what I claim is that it pays to set lambda S equal to 0 for these guys. Okay. So for some of these guys, and what is the total probability in these small guys? That should be less than epsilon. Okay, so let me also write that. So this is less than epsilon, these guys. Now, there can be at most one coordinate where the lambda S is strictly between 0 and 1. So that is the next smallest guy. So let me draw that a little larger. So for this probability, it can happen that the optimizing lambda S is between 0 and 1. It can happen for this guy. Yeah. And for the remaining coordinates, lambda s is equal to 1 for all the higher guys. So let me, so let's say I draw another coordinate out here. So for these guys, lambda is equal. Can everybody see this diagram? I don't see any feedback. Can everybody see this diagram? Yeah. So this is the geometric picture. Pretty much. So the proof basically tries to achieve this geometric picture without loss of generality. So I'll give you some of the ideas of behind the proof, and you can go home and open your books and work it out. It's not difficult. Okay, so let us start. So let us say I have an optimizer for this linear program. Okay. Some setting of the lambda s. Now let's look at lambda s for the smallest guy out here. Okay. Now, suppose I decrease the lambda value for the smallest guy by some, let us say, theta, and increase the lambda value of one of these higher guys by the same theta. Okay, so the summation lambda still remains the same. The value of this objective function remains the same. But what has happened? What has happened is that this constraint only gets nicer. So remember, this is the success probability of correct decoding. This gets only nicer because I've removed theta from the smallest PS and supplied theta to a larger PS prime. Right? So that can only increase this. So given any purported optimal solution, I can get another optimal solution where I have decreased the smallest lambda. So I keep doing this. Okay, so that's the strategy. I'll do this till I zero out the smallest lambda. Then I'll go to the second smallest guy in terms of probability. I'll zero out the lambdas for the second smallest guy. Then I'll zero out the lambdas for the third smallest guy. I'll keep doing this. Okay. So is it clear? Any questions?
So that's why there is this one guy left who is between 0 and 1.
Yeah. I'm coming to that. Yeah. So just this part. So when does this process stop? Okay, I mean, here it looks like I'll zero out everything and then there's some contradiction. So this process stops when, let us say I come to this special guy out here, and why is the lambda strictly between 0 and 1? Why couldn't I decrease it further? So when I come out here, remember I've zeroed out all the smaller sample points. So the tail has been entirely zeroed out. Okay, and everything is fine. Summation lambda is still the same. This success probability has only gone higher. Okay, now I try to decrease this, but I cannot even decrease it by minuscule theta because all the higher guys are already 1. There is no space to even decrease by a very small quantity. So that's what can happen. Okay, that is why this quantity for this sample point is stuck to some value between 0 and 1. And everything to the left of it is exactly equal to 1. Okay. So this is how the picture stops. Is this clear to everybody? Okay. Yeah.
So basically, we are like filtering. We're like filtering it, right?
If you want to call it that, yeah. So we are reshaping the vector lambda. Okay, we are reshaping the vector lambda by zeroing out lambda s for the
Smaller probability.
Yeah, for the smallest probabilities s. Okay, and we keep doing this till at some point we are forced to stop because of a situation like this. So now the question is, where are we forced to stop? Okay, so remember, I made another claim that if I look at this tail, the tail which has been zeroed out, that is less than epsilon, less than or equal to epsilon. So how do I prove that? So the point is, let us look at these guys where lambda s is exactly 1.
Pranab, can I just ask one question? So my stopping rule here is that I'll keep on pushing the mass to the left until I find that point to the left of which everybody is 1. That's my stopping rule, right?
Yes. Yes.
Okay.
Yes. Yeah. This is an important part of the proof. I invite further questions. Okay, no? Okay, so that's the stopping rule. So what remains to be proved, okay, is that this tail which I've zeroed out, the lambda S's which have been zeroed out, they will add up to something less than or equal to epsilon. Why is that the case? So let us see. So these guys, okay. So these are the guys where lambda S is equal to 1. Now, what is the contribution to success probability from the left lambda S? Okay, so that is exactly summation PS. Okay, and remember the reshaped lambda that I've got is a feasible solution. It does satisfy the success probability larger than 1 minus epsilon. So what have I got? So the left guys, the summation of their probabilities, okay, is something, and then there is one more guy out here. Sorry, this borderline guy where the lambda S is between 0 and 1. Okay, let us say here the lambda S is something between 0 and 1, but let us say I overcompensate, and I also add the probability of this borderline guy to the left hand side of this inequality. Okay, so I'm looking at the sum of the probabilities of the leftmost guys where lambda S is exactly equal to 1, plus I'm looking at the probability of this borderline singleton guy. So already this will be greater than or equal to summation PS lambda S, which I know is larger than or equal to 1 minus epsilon, right? Because the reshaped lambda S was still a feasible solution. We have seen that before. Okay. So what do I conclude? I conclude that the lambda is equal to 0 are the smallest probability guys which are zeroed out, and they can only eat up at most epsilon, maybe even less. So now you see the connection between the solution to the linear program and the definition of Hmax. So what is Hmax? I just look at the number of guys to the left. So lambda is equal to 1 plus maybe this borderline guy. So the log of this number is HFS, right? Okay. Any questions about this? So let me write the record. What is this? Lambda.
So just to make sure that I'm clear on this, so you essentially start from one feasible solution, then you start doing this exchange argument, and you say that okay, keep on zeroing out, and you have some sort of a stopping rule. Then you say that okay, since I had started with a feasible guy and I ended with a feasible guy, and that the feasible guy that I ended with, he looks like all ones, then something in the middle, and then all zeros. So so by the constraint by the LP constraint, I can say that whatever mass that has been left out, that has to be at most epsilon. Can't be
correct. Correct. Did everybody get that? Yeah, that's the proof. Okay, lambda, the vector lambda always remains feasible means it satisfies all these constraints. Okay. Success probability is larger than 1 minus epsilon, and of course, all the individual lambdas are between 0 and 1. Okay. Okay, so that's the proof. So what have we got? So E is the number of coordinates with non-zero lambda S, which we just argued. So so this means that log E is by definition is H epsilon max S, and so we have now proved out a one-shot noiseless source coding theorem that the minimum number of bits, okay. So the minimum number of bits, we remember there was this very nice deterministic decoding and encoding strategy, almost naive. It's almost too good to be true. So that gave me ceiling of H epsilon max. So let us say it's less than H epsilon max plus 1. And I know that mod E is larger than yeah, summation lambda s. Okay, and so I get that mod E is larger than H epsilon max. Okay. So that's it. Any questions? No? Okay, so it's amazing how the naive strategy turns out to be nearly optimal. It is optimal to within 1 bit. Okay. So recall that this is much. So let me go back to the. Recall that this is much better than what Shannon proved, because Shannon, in Shannon, the lower and upper bound was off by quite a large amount. I mean, the gap between this is n HS times delta. Okay, which is much larger than 1.
It's a multiplicative difference between multiplicative and additive.
Yeah, multiplicative in number of channel users, and there's a H of S and all. And here, amazingly, it's just 1. So this is what one-shot analysis done the right way buys you. Okay, so I think because of this joining problems, I'll skip this part. It's not very important. It will be there in the slides. So it is fun to analyze the dual of this LP. Okay, so people who know linear programs, I mean, for every linear program, I can write another linear program which is called this dual. So the dual of this linear program you can check looks like this. And the weak duality, which I mean has an elementary proof, I've even given it here for the record, says that the optimal value of the primal solution, which is a minimizing LP, is larger than the optimal value of the dual LP, which is maximizing. And then one can give a similar argument to find out which is the optimal value of the dual LP. And I mean, you can do all that, the same kind of shifting argument. So now the vector of unknowns is mu. So there is mu0 and then mu s. Okay, so the earlier vector was lambda, so there was a lambda for every s. Now there's a mu for every s, plus there is another mu called mu0. But you can work out by similar shifting analysis, find out explicitly what the optimal mu vector looks like, and you will see that the max value of this is exactly the min value of the primal LP, which is not surprising because the strong duality theorem, which says that the primal and dual optimal values are equal under very mild conditions. And you can again conclude that the smallest value of the mod E is this 2 to the H epsilon max. But let's go to something which is more interesting. Okay. So we did one-shot noiseless source coding. The question is, we remember a different lemma from the IID setting. So can we recover the IID setting from here? Okay. So this is the traditional IID setting as you have seen, and we can compress down to n HS times 1 plus minus delta, right? There's a gap between the lower and upper. Now what I can do is I can view it through the one-shot lens. So I will think of the source, a new source. So instead of thinking of the source here as S, I'll think of the sources as S to the tensor power n. Okay. So call it a super source if you want. So my super source is made up of n independent copies of the original source, but that's it. So the super source is single source. Think of it in the one-shot fashion. Apply the one-shot encoder E, which you have just seen. So it will compress down to something. And what I'll get is H epsilon max Sn, and maybe up to plus 1 bit extra. So the question mark says that this lies between H epsilon max Sn and H epsilon max Sn plus 1 within 1 bit. Okay. Now, how do these two quantities compare? Okay. And I mean, maybe one may believe that this is so naive that definitely, I mean, this fancy thing with typical sets and all this should actually be a better result than this in something. But as you'll see, this is far worse. Okay. So how do you see it? It's not so difficult to see. So consider a real valued random variable S prime. So this random variable takes the real value, negative log PS1 minus log PS2, so on up to minus log PSN. So what is S1, S2, Sn? So this is an output from the super source S to the tensor power. And what is the probability of outputting the tuple S1, S2, Sn? It is just the product of the probabilities. Remember, the super source is made out of NIID copies of the basic source. So the probability of outputting this real value is just given by this expression, PS1, PS2 dot dot PS. Okay. So what is the expectation of the random variable S prime? Linearity expectation. So I just get n times expectation of negative logs PS, and this is nothing but the Shannon entropy of HS, right? So let me flash the Shannon entropy, right? So remember, the random variable is negative log of PS, and I'm taking its expectation over the distribution PS, which is exactly this, and this is called entropy, Shannon entropy. Okay, so the expectation is exactly n times h of s. Now let us compute the variance of this random variable. So the variance of this random variable. So remember, this random variable is made out of n IID copies of the basic random variable S. So because they are independent, I can use additivity of variance for independent random variables. Okay, so I get n times the variance of a single copy of the random variable. So remember, the random variable is negative log PS. Okay, so I'll give this a name. Okay, so this is a new quantity which you may not have seen in traditional information theory course, but it is very useful for us one-shot guys. So the variance of the source is defined to be the variance of this random variable, negative log PS. And its expression is the usual thing. So the variance is the expectation of the random variable squared, okay, minus the square of the expectation, which we know is h of s. Okay, right? So is this definition clear of var s? Any questions? Okay, so let's go ahead. So once I have the variance, I can use Chebyshev's inequality to study the concentration of S prime around its mean. So Chebyshev tells me that the probability that S prime varies from its mean by more than this quantity is less than epsilon, right? So what was the Chebyshev expression? It is the variance divided by the deviation squared, right? So you can work it out. Remember, the variance is n times where did you go? The variance of S prime is n times var s, okay, and then divided by this square, you get epsilon. Okay. So what is this telling me? So let us say I start off with the source S. So sometimes I'll write S to the n instead of S to the tensor power n. So this is n IID copies of the base source. So zero out, the smallest probability is in S to the power n that sum to at most epsilon. Okay. So remember, this is exactly the H epsilon max Sn strategy. So suppose I apply that strategy. I zero out the smallest guys. Okay, that sum to at most epsilon. So now what can I say about the least remaining probability? Right. So I've zeroed out the tail, and now I look at the smallest sample point which has not been zeroed. So what is that what is the sample point? Let's call it S0 to the n. Remember, here the n just indicates that this symbol is an n tuple. It's a reminder that the symbol is an n tuple. So the least remaining probability satisfies this quantity. This is what I claim. And this follows from here. Okay, so what do I know? I know that. So what is this?
One second. Don't we have to zero out those guys which lie outside this event?
You can, but I mean, you don't have to work so hard. So I'm getting to that. Okay. So you don't have to work so hard. Okay. So what is this Chebyshev concentration bound telling me? It tells me that if I zero out those sample points such that the S prime is larger than NHS plus blah blah, if I zero out those guys, then I would have lost only epsilon fraction of probability. Okay. So, but what are these guys? What are the sample points where S prime is larger than this certain threshold. So remember, S prime large means the probability is small. See, remember, this is S prime. This quantity being large means that the corresponding probability is small. So zeroing out sample points with large S prime means zeroing out sample points with small probabilities. Okay. Now what I've done, if I've zeroed out the smallest probabilities that sum to at most epsilon, okay, that means I may have zeroed out some of these guys, okay, that satisfies this threshold, but definitely I cannot zero out any guy which does not satisfy the Chebyshev threshold. And the smallest sample point which is not zeroed out will not satisfy the Chebyshev threshold. So that's why the inequality is less than or equal to NHS plus the deviation. Is this argument clear? To everybody? Okay, yeah. So pause and think about it. Maybe it will help to again draw a diagram with points and what you're zeroing out. Okay, so let us believe for now that the least remaining probability satisfies this expression. Okay? So this is the least remaining probability. So what is the log of the size of remaining support? The log of the size of remaining support is at most 1 upon the least remaining probability, right? Because there is some 1 minus epsilon there, fudge factor, which will not affect this much. Maybe you'll get a log of 1 minus epsilon term somewhere here, but anyway, so I'll correct it when I put up the slides. So why is that? Remember the remaining guys add up to 1 minus epsilon probability or more. Okay, so how large can the support be? If the support gets too large, remember the smallest probability in the remaining support is at least this. So if the support gets too much, then the probability will exceed 1. That is not allowed, right? So that's why I get this bound. So the log of size of remaining support is at most this much. Any questions? Okay, next. So, okay, so let's clear this for a moment. What was the traditional proof telling you? The converse proof says that I cannot compress to less than n hs times 1 minus delta. The one-shot proof says that I cannot compress to less than h epsilon max sm. And converse and what the achievability, the traditional proof says that I can achieve n hs times 1 plus delta. The one-shot proof says I can achieve h epsilon max s to the power n plus 1 bits. But how large is h epsilon s to the power? It is nhs plus a quantity which depends upon square root of n. Okay. Whereas here the plus is n delta h, which is much, much larger than the square root n. So this is what one-shot theory has brought. Just the simple naive analysis. Okay. A little bit of Chebyshev has brought you that I can compress even better. So it is NHS plus a little bit amount, but that little bit does not grow linearly in n, which was not known before. It actually grows as square root of n. And what are the parameters? So I get this var of s, which is the probability of the property of the probability distribution, and then there is a mild dependence on the error probability of decoding epsilon. Okay. So this already we can see with very elementary techniques, we are learning something new. In fact, you can go further. So we'll see later in the course when you do the so-called second order analysis. So second order analysis is basically this term, the square root n part. So that can be analyzed very precisely, and we can say that h epsilon max s to the power n is exactly nhs minus this quantity, and the dependence on epsilon can be made very precise. So here the dependence was rather bad. It was like 1 over square root epsilon. Here the dependence is phi inverse epsilon. So I'll tell you in a moment what it means. And finally, so this is an accurate analysis of the second order. And what is the lower order? The lower order grows very slowly with n. It only grows as log n. You do n iterations, okay? To first order, it is n times hs. Second order, it only grows as square root of n. Third order, it only grows as log n. And the order here will depend on the properties of the base distribution epsilon. It will depend upon your error probability, I mean, depend on S and epsilon. Okay? But that's it. And here you can have plus minus. So there's a lower bound, which is the minus, and there's a upper bound, which is the plus. So if I can prove this, what does it mean? What was the converse? The traditional converse said that I cannot do better than NHS times 1 minus delta. Now I know that I cannot do better than NHS, and as you'll see, this is actually a positive quantity plus something, which was completely unknown before. Like one would have thought that one might be able to do slightly better, better than NHS. I mean, go below NHS, but no, you actually cannot even reach NHS. You are stuck out. Okay. The reason this is a positive quantity is that for small epsilon, phi inverse epsilon is a negative number. So what is phi x? So this is the cumulative distribution function of the Gaussian. So take the Gaussian with mean 0, variance 1. Look at its CDF. So this is the Gaussian with mean 0, variance 1, the probability density function. So CDF is, suppose I take, I sample according to the, suppose I take a sample according to the Gaussian, okay, sample x. So what is the probability that the sample t from the Gaussian lies below a certain real number x? So that is phi of x. So that's what happens. This integral is minus infinity to x. Should be that. So this captures the probability that a sample from the Gaussian lies less than or equal to x. Okay. So as you can see that if x is minus infinity, phi of minus infinity is 0. Okay. And as x gets larger and larger, as x approaches plus infinity, phi of x approaches 1. So it's a nice sigmoid curve going like this. And this is the inverse of this function. So given a probability threshold epsilon, okay, so phi inverse epsilon is the x such that the probability of Gaussian giving a value to the left of x is less than or equal to epsilon. Okay. So that is the meaning of phi inverse x. So you can see that phi inverse of half is 0. Okay, that is here. So this is half. Phi inverse of half is 0. So for small epsilon, phi inverse of epsilon is a negative number. So that's why this is a positive quantity. So it is slightly worse than NHS. Now, this result can be thought of as a sophisticated asymptotic equipartition theorem. Why is that? People who have done classical information theory earlier, you have studied equipartition. So that's basically properties of typical sequences. The probabilities of typical sequences approach 2 to the minus n times the Shannon entropy, things like that. So this is just a more sophisticated thing, that other entropic quantities. So what is H epsilon max Sn? So in a sense, it is the smallest non-trivial probability of interest. So the very low probabilities are not of interest. I remove the very low probabilities, the tail. I shave off the tail so that at most epsilon goes off. Then I look at the smallest surviving probability, this piezo out here. So the smallest surviving probability is roughly what is, I mean, you take the negative log of that, that is roughly what is H epsilon max.
Just one thing, isn't that H min? Shouldn't this be H min?
No, this is H epsilon max. H min will be the largest probability. Okay. So this is the smallest probability. It's called max because I take the smallest probability and I take the negative log, that becomes a large number. Okay. So actually the notation is suggestive. The Shannon entropy, I mean, if you recall, the Shannon entropy was the expected value of negative log of PS. So it's kind of like the expected value of this random variable. Then the largest value of this random variable is H epsilon max. There, after I do the shaving, after I throw the trivial parts, and the smallest value of this random variable. Okay, so smallest value of this random variable means the largest probability will be H epsilon min. So the epsilon, again, I have to do some smoothing, but you can imagine what smoothing I'll do for H epsilon min. So I'll throw away the largest few guys, which sum up to at most epsilon. Okay, and then that is the largest non-trivial probability of interest. So that is H epsilon min. So now you can believe that the Shannon entropy lies between the smooth mean entropy. I mean, it is lower bounded by the mean entropy and upper bounded by the max entropy. So that the notation is very suggestive. So this quantity is larger than the Shannon entropy, but if I go to the IID limit, that is the asymptotic equipartition, it approaches the Shannon entropy and we now have a very, very precise idea of how it approaches. Okay. So it's a sharper understanding than the traditional IID bound of n HS times 1 plus minus 10. Any questions? Okay, so we'll finish with this. So, okay. I hope you are sufficiently excited by this invitation to one-shot information theory. So let's take a sneak peek ahead. So what else we'll do in the course? So I recap, one-shot is the most general setting. I hope I've already convinced you by showing how from one-shot I could derive and even improve a result in the traditional IID setting. So the one-shot setting similarly implies result in the asymptotic non-IID or the information spectrum setting. And in fact, it goes both ways. So many one-shot ideas have been adapted from the non-IID theory, which was pioneered by Hahn. It is not very well known, but it's probably becoming more well known now that one-shot is coming into shape. But nevertheless, the non-IID theory is still asymptotic. So you'll see expressions like everywhere you divide by n and take limits. But in one-shot, we're not going to do that. We're not going to divide by n, and we are not going to take limits. We are going to use explicit expressions like this, if required for the IID analysis. Okay, we'll keep track of every epsilon, every delta, and we'll be as precise as we can. Now, the one-shot theory lends itself to strong quantitative versions of asymptotic equipartition theorems. So it often gives better understanding than known earlier in the IID setting. So second-order rates, which I've shown you, and later on we'll see that there are new strong converses that I can prove. Okay, so converses have been known in the IID setting, but strong converse essentially means that if you go above a certain rate, then the error probability approaches 1. So this is what would be a strong converse. A weak converse would be the error probability is not cannot approach 0. The strong converse would be 1. So sometimes you have a better understanding via the one-shot ideas. And the smooth one-shot entropy. So all the one-shot theory works with the smooth quantities, H epsilon max, H epsilon min, so on. So the smooth one-shot entropies have applications to other areas like cryptography and computational complexity. We'll see some applications in this course. Okay, so I'll stop here now. Any questions? Okay, no. So then I'll stop the recording.